Okay, welcome to week 2. The what I wanted to do this week, I wanted to go over some of the reading material that we went through in Kuhn and Johnson from last week, and also a little bit of this week. We're going through a lot of readings, so it's difficult to go through all of it. So I'm just gonna pick a little bit here and there, and then try to do some supplementary writing, to post on my blog or something else to kind of fill in more of the details. So in Kuhn and Johnson, one of the data sets that they have is German credit ratings. And I'm actually involved in the P2P lending space. I have some credit models that I developed last year for that, for the Prosper platform. And this year, I wanted to get involved a little bit with Lending Club. And so I thought that this would be a good use of, of looking at some of the methodologies in the book and applying it to this data set. So I've already downloaded some data, and I'll distribute this PDF. I need to clean it up some more, but I'll distribute this later. But I downloaded some of the active listings that exist on Lending Club. Basically, like the way these P2P lending platforms work is that you've got the short description is that they essentially disintermediate banks. And the lending platforms become a marketplace where they originate loans. Borrowers or prospective borrowers go onto the sites, apply to borrow money, and then those are called listings when they request to borrow money. And then that information is put onto the site, and then investors can pick through the different listings and decide to fund any of the borrowers. And so there are actually two models that are involved. One is for fractional loans, where you can choose to just fund a portion of a loan, or you can go into the whole loan market where you buy whole loans outright. And you would do one or the other depending on how much capital you have. If most retail customers do the fractional lending because that gives them more diversification than if they were to buy purely full loans. So what I wanted to do is just kind of walk through some of the methods. I mean, you did some of this in the homework, but I thought it'd be nice to do it for another example, and then see how it evolves into some of the other analyses. Because I flipped through some of the homeworks that were submitted, and I don't think that I saw all of the pieces that were included in Kuhn and Johnson. So the first thing that you want to do in this model process is really preparing the data. And if you look at the loan data, and I'm gonna kind of switch between windows, so we'll see how easy or difficult that is. So let's see. So we've got just an R shell here. Let's see. So this data frame contains all the listings that I downloaded for today, and there are 490 of them, and there are 86 columns. So just to kind of give you a sense of what this looks like before we even do anything, you can see that there's all sorts of different variables and fields that are contained in here. So there's loan ID and member ID, which uniquely identifies the loan, and then also the user that's requesting the loan. You've got the loan amount, the funded amount, how long, the term of the loan, interest rate, and then so on and so forth. So one of the things that just from looking at the column names, we can already identify that some of these columns aren't really useful for modeling, right? Like you can't really infer any information from like the loan ID or the member ID because they're just unique identifiers. Similar thing can be said of some of the date fields, because they really have no bearing on credit quality either. So even before we do the analysis, we need to clean up a lot of that stuff. So I wrote some routines to do that, using some of the techniques that are discussed in the book. And I'll switch over to the code window here. Can you see this okay? Is this big enough, or do I need to increase the screen size?
Okay for me.
Okay, so we'll just keep it like this. So I wrote a few different functions here. One just loads the listings that we want, and then I actually added the data provides a FICO range low and a FICO range high, and I decided, well, maybe I'll just make a mid measure instead. So that's what that is. What we're talking about though right now is really the second function called filter. And you can see that I've got a whole bunch of different things going on here. The ones that come from the book are really the near zero var function, and we can run that and then see which columns are which columns have basically near zero variance, and we want to remove those. I also do a few other things in here that aren't really listed in the book, but are just kind of convenient to do at this stage of the analysis. The first one is because we've got all these sorts of different fields in here. Some of them are factors, some of them are like description and purpose, and they're not really useful for doing any sort of analysis that we want. And so a simple way of just getting rid of those columns from the data frame are just to seek all the columns that fit that have a particular class associated with them. And so this AnyTypes function is actually in a package that I wrote called Lambda Tools. And okay, I'm just going to show the whole window. I think that'll be easier. So basically what this does is you can do AnyTypes on a data frame, and it'll show you all the types for each column. And so then it's just an easy way to see what the what the composition of the data frame is. You could do the same thing using like the str function, but I find that sometimes that'll print out a lot of stuff when I really just want the types. So a lot of these things, like the accepted date, they didn't parse into date times, so they're just character strings. View status, purpose, some of the state, the location, geography information. So that just gets all stripped out, and that's a fairly fast process. So I go through that process, and then another thing that I do here, just briefly, is I get rid of any columns that have NAs. And this is just for convenience. I wouldn't recommend doing this in the real world, and it's actually one of the questions near the end that I want to talk about. But in terms of just getting up and running where you can actually identify stuff, it's easy to just eliminate those columns and not really worry about it. The next step of this function is then using the find correlation function to find the variables that are highly correlated, and then you can omit those as well, right? And then the last little bit here that I do is I create a keep and a drop, two variables, one to explicitly keep columns and another one to explicitly drop columns, which is just useful later on when if I want to add certain columns that get thrown out through this process, then I can either explicitly keep them in the data set, or if they don't get dropped, I can just say, okay, drop it. And so that gives me a convenient interface for dealing with some of this stuff. So when you run this thing, one of the things that you'll see first little bit is this, the finding all the columns with very little variance, right? So for the example, I just put that into a variable and then use that to index into the column names of the data frame so that I can print out explicitly which columns those are. The oh, this is in the wrong order, which is why this isn't working. We can actually examine these and then see, what this looks like, if that works. And you'll see that we've got the not verified column or category is the majority of the variable. So this kind of falls into that classical case of very low variance in that variable, so it's not going to do us much good. I did another one just to show you that it doesn't always have to be categorical, but this one is, in theory it would be like continuous values, but it turns out that there's only two values. 489 of 490 are actually 0, which is good, I suppose, and then the other one is 5. So this actually tells me that I think that the field, like the values in this column might actually not be correct, because it seems, I don't know, it seems awfully low to have only one to have only one borrower that has like a delinquent record for their borrowing. So the right, so the find correlation. This is really great. That you can just use this package very quickly to work through and identify all those columns. And one of the things that you'll notice is that what popped out of this is that my FICO mid and the FICO range high were both identified as being highly correlated to another variable, and probably that's going to be the FICO range low. So this is a situation where if you want to use one versus another, it probably makes sense to explicitly keep the one you want, drop the others. Otherwise, one of these, like a built-in function that does it automatically, you're not really going to have the control over which one is going to be dropped, right? So that's that's one of the reasons why you would want to have a little bit of fine-grained control on like that filter function. And then just for comparative purposes, I wanted to show the difference between when you do a cutoff here of 0.75, which is going to be the correlation, the minimum correlation to throw things out, and then if you increase it to 0.9, then you're down to 9 variables that you're dropping out instead of 22. And the interesting thing about that is that, again, FICO range high and FICO mid are both kicked out. So that tells us that the FICO scores, there really is no point in showing both of them, because they're so highly correlated that that there's not additional information there. So if I do the actual filter, what you'll see is that, oh yeah, I actually changed the threshold. So here I said 29, but there are actually 36 variables now. Now I wanted to plot out the core plot that the book has. Very nice plot, but unfortunately it didn't really work out here very well. So we'll do it we'll do it in the shell. And one thing that I discovered is that you have to be careful. Here, let me just copy and paste it. You have to explicitly pass in the package name, because what I discovered is that both the partial least squares package and the core plot package define a function named core plot. So, sorry, hold on. I just do it this way. I know my functions work. Okay, so this is the correlation plot for the clean data set. And what I was saying is that you have to explicitly specify the package name because there are two libraries or packages that actually use that same variable. And if you don't, then I was getting a very different plot with a whole bunch of warnings, and it took me a little while to figure out why that was. So just be aware of that. So this is a very interesting, visualization of correlations, which is actually quite useful. With it, you can see the nice thing about the function is that it actually reorders the variables according to the correlation structure, and so it kind of clusters things together so that it's easier to see where you have groups of variables that are correlated. So what we see here is that there's a little group, a few variables that seem to be highly correlated or highly inversely correlated, and then a few over here, and then in the center you have a whole bunch that appear to be correlated together. And in my experience, this has been this has held for Prosper data as well, where you have all these variables, and they actually claim that they make available over 500 different data points per listing. But what I discovered is that not a lot of them have unique information, despite the large number of points. And so this kind of bears the same conclusion. So let's see. So right. So what I wanted to do is then show what happens if we don't remove the correlated variables. It's something that you kind of take it on faith in the book that this is the process to follow. And I think that they obviously know what they're talking about, but it's also good to kind of see it for yourself to get an idea of, yeah, does this make sense to me, or is it or is there something funky about the conclusions? So that's what this does. Is that let me actually do both. Okay, so this is the trimmed version, and then this is the larger one. So what that shows. So now we can kind of see here's the FICO mid, the FICO range low, and the FICO range high, and as was told by the find correlation function, wow, they're all pretty highly correlated. So yeah, so it's no wonder that that those are being removed. And so it seems to be true that by by filtering those things out, we can have a simpler data structure and still have similar information, right? So I think that this is a pretty good way of kind of convincing yourself that these the information that you're removing, it does indeed make sense. Right. So does anybody have any question for this part, or?
Why do you remove all the highly correlated variables rather than just some of them?
Uh,
Like with the FICO ones, why do you get rid of all three rather than keep one if it's it has different correlations with the other variables?
oh no, you keep one. The
What do you do? Okay.
yeah, the FICO range low is here. Yeah.
Okay, sorry, I thought you got rid of all of them. Okay.
No, no. Yeah, that then we definitely be throwing away information.
Yeah, okay. All
That
right. Sorry about that.
yeah. The oh, what's the annoying part of R? Sorry, I had to close the window at one point. The oh, okay. The any other questions on this part? Okay. The that's fine. One of the one of the other things that since we're talking about this, one of the other things that you have to be careful of when uh, doing this sort of analysis from this sort of data is thinking about a little bit about the causality of how the variables are constructed in the data set that's provided to you, and making sure that um, that you're not using the variables incorrectly, right? And I'll get into that a little bit later, but I wanted to just kind of plant the seeds for that discussion as we continue along. So one of the things that I mentioned in this write-up is that the data set that we're using, because they're the active listings, you can't actually you can't actually use them to do loan selection in a traditional sense, because usually you're looking at like the training sets that you normally have would already have like loan performance, and so you would be able to model whether or not for a given loan and all the attributes associated with that did that loan default, and then what you would be predicting is the probability of default. But since these loans aren't actually loans, but they're listings to become loans, we have no information about the probability of default. So it it's somewhat of a curious choice to begin with for the modeling. The nice thing though is that there are only 500 listings, whereas like if you take the historical data set, it's much larger, and then you gotta everything becomes a little slower. And some of the SVMs on my poor little laptop already took a little while to do. So um, okay, so so I decided to do two different analyses using this data set, and the first one is seeing whether or not the variables that are contained in the filtered data set have enough information to predict the grade of the loan. So I don't know how many of you are familiar with like the way loans work, but usually, it's kind of like how the S&P, like the Standard and Poor's grades like corporate debt and like government bonds. There's like a letter grade that indicates credit quality. So Moody's uses like capital A, lowercase a, and things like that, whereas like Standard and Poor uses all capitals like A and B. Um, and so the Lending Club does something similar, where they have 5 letter grades, and then they have subgrades within each of those. And so the grade itself is just A, B, C, D, E. And what I wanted to do was to take the grade and then see whether or not I could predict it based on the other variables. So again, I use that filter function that I mentioned earlier. And then here is an example of actually specifying that I want to keep the grade, because grade is actually a factor. And so based on the way the function works, it would just strip that out, because in order to plot the correlation matrix, I wasn't getting it to work very well with the factors, so I just decided to remove them all. So um, So this way I keep that variable in, and then I can do the training routine, which is calling the train function and then specifying the formula for what I want, and then the data set, and so on and so forth. So this is pretty much straight out of the book, except for I'm using a different data set. The nice thing is that you can see how, for the most part, you can use basically the same syntax and then change the method, and it'll work more or less the same. Of course, if you have the wrong data, you're not guaranteed any performance, but at least the code should run, right? So this is what I did for using the support vector machine. And if you look at the grade, let me just do that very quickly. Oh, okay. So you can see that there's 109 A's, 338 B's, and 43 C's. So it's not a horrible, not the greatest balance, but it's also not horrible. So, presumably, like in the larger historical data set, you'd have a better balance of things, but or it would be easier to balance it the way that you want because you have more data. But for this, we'll just leave it as is. And when we do that, we run it through. We can plot the fit of the SVM, and then we can see where we can see what the accuracy is and how it varies based on the cost function, right? So I don't know if you picked it up in the book, but this tune length variable is essentially tells the train function how many iterations to run through with the different costs associated with it. And so it starts off at I think 2 to the minus 2, and then so like 1/4, and then it goes up to whatever the last one would be, incrementing up. So that would be 2 to the 7th, right? And so that's how you see what these steps are based on what your tune length is. And so we could do a tune length of 20, but based on what this looks like, it doesn't look like there's going to be any more effect if you increase the cost of the cost variable on there, because it seems to max out very early on, and I believe at 4. And so that tells us, that essentially the classification is fairly stable in that regard, and when we want to use it for actually applying the predictions, we would use it. It optimizes it right here, and we're getting about 83% prediction accuracy on that, which I think is I think it's kind of what you would expect. It's not great, but for like out of the box without really doing any sort of tuning, it's not bad, right? So the again, what I wanted to do, in the same way that I have one version of the correlation matrix with the correlated variables and then one without, I wanted to again do that sort of same comparison, but this time using the SVM. And so the second call here, I'm doing the same call, except for I basically told my filter function to not throw out the highly correlated variables. And we can see that the shape of the two functions are more or less similar, but what's different about them is that we've gotten almost up to 90% now on the accuracy. And we'll go back at the end. We'll talk about why that is. But this may seem surprising at first, but if you think about it, it shouldn't be surprising. The second part of this is thinking about it in terms of regression and whether or not we can predict the expected default rate based on based on the variables. So this time I did a little bit of pre-processing. I got rid of the grade because this is what I was talking about, where you have to understand how the variables are created. Since the grade is the grade and also the expected default rate are provided by Lending Club, and they're not inherent to the borrower. If you use the grade as a variable to predict expected default rate, it's going to dominate all the other predictors because of the fact that they're already highly correlated, right? Because the letter grades are an indication of the risk of the loan. So I'm not including that, and then I'm also dropping the funded amount because, well, essentially because when I did the analysis, there actually showed that there was actually like a significant. It turned out to be highly significant, and I kind of decided that's probably a spurious relationship because how is the funded amount, like the funded amount is essentially how much of the requested loan size has been pledged on the platform. And to me, I couldn't really justify any way that would be correlated to the actual default rate of a borrower. If you had a time series view of that, then it might be an indication of how much perceived risk it had. But just at a point in time, it seemed very difficult to expect any information from being there. So I just dropped it. So that said, here's the train call. This time, I'm just using the linear model instead of an SVM. And this didn't, oh, right. Let me just run this, because otherwise. Oops. Okay, so I just did a summary on the model, and then you can see all the variables that are in play. It's showing that the term is actually significant, as is the installment. So again, these to me seem to be spurious. Lending Club actually says that the term, well, not so much the term, but the loan size, they penalize large loan sizes in terms of the grade, which kind of makes sense. And so the installment should be the length of or the size of each payment, I believe, and then the term is the number of months for the loan. So those are both going to be correlated to a certain extent to loan size, because people who borrow, say, $20,000 are unlikely to want to pay that off in 2 years. They'll probably choose 5 or 6 years, and so then that becomes that becomes another indication of risk. Like if you're familiar with fixed income, that ends up having a higher duration, and so you're susceptible to to other factors there. So unsurprisingly, the FICO score is also considered significant, and then you've got a few other things that are not as significant but appear to have some effect overall. So that's kind of interesting. Again, as an initial analysis, I think it's not bad what it's showing us. However, if we start to look at the the fit, one of the things that the book kind of emphasizes is that you really need to think about, the error on, or the distribution of the error on the residuals, right? So I created some functions that just plot that out the same way that they do in the book, and then looked at it for this data. The example they have in the book, they show the two plots for observed and then the residuals, and then they're like, it doesn't look like there's anything particularly worrisome in those results, so we'll move on. So, the first question that I had when I read that is, be nice to show one that looks very worrisome so that people have a good sense of what that means. And so our credit data is actually very nice in that regard, because we have a distribution of residuals that looks, that appears very worrisome to me, because it doesn't appear to be distributed normally at all, right? So what's interesting is that you get these bands in the predicted and observed relationships, whereas if they were, if it was a good fit, obviously it would be following this linear line, and instead we'd get these bands across each one. And then similar thing happens on the residuals, except for it seems like it's been rotated. And I haven't actually looked at why that rotation occurs, but that may actually provide some insight into why it's not a very good fit. And I also did the same thing. Did I put it on here? Yeah, oh yeah, here. So I did the same thing with the partial least squares. And let's just do that real fast. Hopefully it's fast. While that's running, you can see you can see how this one turns out. Predicted and the observed actually don't look very different. It's hard to show it here, but just kind of take that snapshot, and then it looks very similar, but the error terms, as you can see, are very different. And I think that that again is indicative of the way the models are working, and something that I want to explore some more in the next, either in a post or in the next session. But here you can see the the results of the partial least squares and the error associated with that. So we can you can see that there's actually a fair amount of error, which then drops off after you get to around 12 or 13 components, and then drop some more, right? So that kind of gives you an indication of how good the fit is, and also like how many variables you need to explain the variance. So that I guess we have about 15-20 minutes left. What I wanted to do at the end is to unfortunately my questions don't get formatted very well. It's kind of have a little bit of time to do some discussion like last time, and think through some of these questions. So I'm going to just read them all out, and then you guys can decide which ones you would like to answer, and then if we whichever one we start with, let's try to have a little bit of a discussion with it, and then we can move on to another one. So one of them is related to the first part of the class, where I said that I was just throwing away the categorical data and then also columns with the NAs. So one question is, what's a better approach for either or both of those data issues? The second question I had on here is in terms of the correlated variables. So remember I was saying that when we didn't throw out the correlated variables here, we actually ended up getting better accuracy. So the question is, why is that? And is that good or bad? And then the third question is just a little bit more general, just talking about, well, because this is a preliminary analysis, there are a lot of things done either carelessly or sloppily or just not correct at all. And so the question is, can you identify some of those issues and how would you improve it? And then the last one is related to these residual plots, and what are some ideas for actually cleaning this up so that the noise term has a better behaved distribution than what we see right now. So who wants to tackle one of those questions?
I want to take on one of those.
Sure.
Because it was bothering me when I was doing the assignment. It was on the missing data.
On the what?
The missing data?
Yeah.
Throwing away the missing data? Yeah, because I was struggling with it a lot. This is the strategy I was thinking of when I was looking at the data set. So I decided to split it into two. So I would take the ones that had complete data as a training set, and then I was planning on building a model off of that, and then run it on the test data set, which would be the set of data with missing values, and then trying to predict using the model that I created from the training one. And obviously, some of the concerns of mine was maybe introducing a lot of bias into the final model by doing so. But I wasn't sure if I wanted to drop like a whole set of like rows from the data set that we had.
Right. Yeah, so that's a good question. And well, there are two things about that. The first one is, did you install the impute package? It's actually part of Bioconductor. He kind of just like skims over it quickly. It's actually on page 54. So that's the way. Like they talk about imputation and a little bit about how to do it, and then but it's really glossed over. And the key is in this page 54 where there's actually, he says that there's a you can use the impute package, and there's a impute.knn, so you can use like a k nearest neighbors, and presumably there are other ways, like he mentions doing a regression on it earlier in the chapter. So that would simplify the process of actually imputing the missing values. It doesn't answer your core question though, which is, does it introduce bias? And so the question, well, I don't want to answer it explicitly because I want to use it as like a follow-on. Like, how would you actually test to see whether or not there was bias introduced? Either Sharad, if you want to take a stab at it, or if somebody else wants to take a stab at it.
Oh, I'm thinking.
Yeah, okay.
Well, would that be basically whatever data you have that will have more influence? So basically, if you, let's say you have results that would lean towards a certain like answer or certain classification, and because you based off of that, now you created a model that's more biased towards that kind of classification. Whereas if you were to pick a totally unknown, I don't know, a sample, I would say, and you're trying to create a prediction, it will be more influenced because of the data set that you used, even more heavily than if you had ignored the NA points. I don't know if that makes sense.
I think so. I think what I would say is, to a certain extent, it's kind of a trick question, right? Because um, if you remember the way that they characterize like the bias variance trade-off, um, what I was going to send out a link for this web page that I was reading that had a nice description of it in terms of key nearest neighbors. Um, you can look at bias and variance as being synonymous with accuracy and precision, right? And if you think about it from that perspective, for me, I grew up on those terms, so, so it's easier for me to kind of think about it from that perspective. If you think about it from those terms, like the book is saying you can either improve your accuracy at the expense at the expense of precision or vice versa, right? And so it, if you think about it like that, what are you doing with imputation? Well, you're kind of like, if you don't have those values in the first place, you're probably not going to have very good accuracy, right? Um, and so you're going to include those values because you want better accuracy in your model. So by definition, that's introducing bias, right? And so what I think is useful about imputation then is that it's a way to kind of circumvent the trade-off, because you can introduce a bias that's good without necessarily impacting the variance, right? Because you're including additional data points through the imputation, so you may even be able to reduce your variance while also improving your bias. And so that's the way that I'm thinking about it. And I'm happy to hear if other people have different interpretations of it, but that's how I would think about imputation. Is that a thinking sign?
I have a quick,
Yeah.
yeah, I had a quick question about the imputation. I guess my understanding of imputation is that in many ways it's almost like it's a mean estimator of all the values that you observed in your data set. So really, how much bias would you be inputting if it's just a mean of all your observed values?
Well, that's not the only way to impute, though, right? Um, like I think in the book they mentioned doing a regression on it, so that's not really going to be a mean. And then in like that page that I referenced, they talk about using a k nearest neighbors approach, and so again, like you're not so that's more of a spatial way of imputing the data, right? Because you're kind of you're mapping it out in this multi-dimensional space and then imputing the values based on what else is nearby. I mean, you could call it like a mean of those values, but it's not it's not a global mean, right? It's a local mean, and so that will introduce different sorts of biases, right? Like behavior that's very different. Does that make sense? I'm not sure if I explained that very well.
Yeah, that makes more sense now.
It does. And I have another question.
Yeah, sure.
How does it relate to categorical data? Do we just does it just move to classification models instead of KNN, or
Sorry, what was the question? The first part?
the imputation and with categorical data? Do we just change the model? Like instead of using KNN, you use a classification tree?
Yeah, I think you could do that. I don't know. Did he mention that in the book? I mean, I would guess that you could use.
The example was all about the numerical data, so
Yeah.
but the exercise was on categorical, so that's why.
My guess is that you could do you could probably do an SVM on that and then fill in those values. I mean, again, you'd have to decide whether or not the benefit of imputing or yeah, I mean, the benefits of imputing those values outweighs the drawbacks of doing it. And that, that's obviously analysis specific, but I imagine that would be legal.
I tried doing a KNN on that data set, which I think almost all the predictors were categorical.
What's that?
In the homework,
Yeah.
I used the KNN imputation model, and those were pretty much all categorical predictors. So I think you can use KNN as well.
How would that work? I mean, what does that mean for? Can you use k-nearest neighbors for categorical data? But, I mean, I guess if you did the dummy variables, you could do it that way. But like to me, I feel like k-nearest neighbors is more of a technique for continuous data.
Good to know.
Did it accept factors, or how did you encode the categorical data?
I actually didn't even realize there was a kind of the impute package, so I kind of wrote my own, and I don't remember switching that to numeric. I have to take a look at my function again, but I thought I just basically just use the KNN function. I can't remember what package that's in the class or something package.
Oh, James makes a good point. Yeah, you could probably do that. Yeah, he's asking if you could do a majority vote on the k-nearest neighbors. Does the R function have that sort of? Does it have a parameter for that? Wait, what is it? Is it just KNN? Here, hold on. No.
No, I think there was a isn't there a package C50? I forgot which one it is.
Yeah, what library is this in? The
I think it's in class.
yeah, that's what I was looking at. Oh yeah, I just saying classification. Yeah, by majority vote. So there you go. Yeah. Yeah, good. So yeah, so that would work too. Great, we're all learning something here. So, does anybody want to take a crack at one more question before we close for the evening?
I think the one with if you have more predictors, why there's higher model accuracy, isn't that kind of towards the concept of overfitting, that naturally if you have two highly correlated variables, you're just kind of reinforcing something that's already there to an extent?
Yeah, does anybody else have an alternative take, or does that make sense?
Yeah, I figured pretty much the same thing, that you're basically overemphasizing that same variable. If they're highly correlated and you think of them as being representative of the same variable or predictor, you're just basically giving that extra weight.
Yeah. So that's right. Both of you guys are right. So that is the the tricky thing about this is because I'm not using a test set. It's an incomplete view of the modeling process. And so that's one of the issues with this analysis, right? Is that there's there's no way to test out a sample because I'm using the whole data set. So if we left it at this, we would conclude the wrong things because we don't have that. So yeah, that's good. Arthur, what were you saying about the E1071 package?
Yeah, that is for that we have used for k nearest neighbor.
Okay. Oh, great. Great. All right. So, are there any other questions, or anybody want to have any comments?
I noticed a lot of the readings this week, some of the stuff about nonlinear regression models, which I find pretty interesting because we haven't covered it too much in our other classes yet. Is this something we might talk about next week, or should we just kind of keep our questions made to the discussion board and things like that?
Wait, you're asking, can you ask questions about it now, or do you want to wait until next week?
I'm just curious if next week's class, I didn't really look at kind of the syllabus, if next week's kind of meetup would talk about some of the stuff from this week's readings, or is that going to be kind of cover new stuff next week and this stuff?
I don't have an answer to that, but if you want me to do something on nonlinear regression, I'm happy to. I'm kind of.
I don't know. I'm really.
What's that? No, because I'm making these up as I go.
Kind of going through the readings.
We're kind of. I wasn't the original professor for this class, so I'm putting together all the material kind of as we're going. So at least for these classes, right? So I can totally do that if that's what people are interested in. Otherwise, you know. Really, if you guys have requests on certain subjects, I'm happy to like dive into it more and discuss it. Like, I actually think that that's a great way of doing it.
Yeah, well, I guess I just don't know what the other options are right now. I just thought some
yeah, I mean, use the discussion boards to chat. I mean, if you have specific questions that you don't understand, or you want to get more background, I'm happy. I can also, another thing that I can do if you have like specific questions, I'm happy to put together some examples that go into it in more detail, and then put it on my blog or share it somewhere. I mean, since we're talking about that, is like have the past two lectures? Do you guys like this format? Is this helpful to like? Is it giving you more? Like, is it providing a little bit more color to the discussion in the book, or would you like to see something else?
I quite like the format of this one.
I like this format too.
Yeah, format works for me. Good.
Okay. Okay. All right. So I'll keep on putting together this way, and then if I can get the questions beforehand, I'll definitely send them out so that you guys can have a little bit more time. I kind of ran out of time today, so not all of it is as polished as I would have liked. So that sounds good, and we'll see you on the message boards, the discussion boards. Don't forget to provide feedback to other people's approaches from this week. So far, what I've seen has been very good, so I'm very pleased with everybody's output.
Awesome. Thank you.
Yeah. Have a good night.
Thank you.
Good night, all.